Assalamu alaikum. It's me, Hammad Shaukat, and today we will discuss about our presentation on jet dependence of charge particles production in PP-Collision at LHC Energies. Okay, so in this presentation, basically we will discuss about the jet dependence of charge particles, and the charge particles we are taking in our this presentation is we are taking proton and proton. Okay, we're supposed to collide proton and proton, okay, at LHC, okay, with different energies. So for that, in this presentation we are taking the lowest energy, which is the zero point 0.9, okay, TeV, and then we will take the middle energy, that is 70 eV, and the max energy, that is 13 tera electron volts. So we will check the dependence. So this is our report and presentation for that. Okay, so let's start. Here are the outlines. We will briefly discuss. First of all, starts with the introduction. In introduction, we will just start with an overview of the standard model. We discuss what's basically the standard model is. Then we will look after on the fundamental forces of the nature. Okay, and after that, we will discuss about the how charge particle produces. Okay, so this is all we discuss in the introduction section. Then we will move on toward the literature review. In literature review, we will overview about the charge particle produce mechanism. What is the mechanism of production of charge particles? Okay, and then we will discuss about the jet production. Okay, and the HIJING model which we are using for the Monte Carlo event generator, because you know that HIJING is one of the Monte Carlo event generator. So in this presentation, we are using the HIJING model. Okay. Then we will move on towards the methodology, and in methodology we will discuss about basically the simulations using HIJING model. What the simulations we do, I will show you, and what are their results we will discuss in this presentation. And then we will move on towards the data analysis and visualization, how we use the data, how we analyze data using HIJING, and how we construct this data to compare our data with the results. Okay, so this we will discuss in this methodology section. Okay, then we will move on towards the results part. In results part, we will show you our results. What are our results after simulating the hiring model data, and after analyzing the data, what are our results? And the results we will discuss about, we will check the multiplicity, the pseudo-rapidity, and the transverse momentum distribution of proton-proton collision at different energies. Okay, so we are discussing these aspects in our results section. Okay, and finally, in conclusion, we will discuss some summary of key findings and some future research directions. Okay, so this is we discuss, and these are our outlines. So let's move on our first slide, and our first slide is for the introduction, and our introduction starts, as I told you, we will start with some brief discussion about the standard model. So what is basically the standard model is, this is basically a framework that describes the fundamental particles. Fundamental particle means elementary particles, okay, and the forces of the universe. So this is basically so called as the standard model. So how you can define a standard model? This is basically a framework which describes the fundamental particles, you can say that elementary particles, and the forces between them, or you can say forces of the universe, because all the matter in the universe is made up of fundamental particles, okay, and forces between them. So the elementary particles are includes quarks, leptons, okay, these are the fundamental particles, okay, and the force carrier between them are like gluons, okay, force carrier of gravity, and photons, which are the force carrier of electromagnetic wave. Okay, this is some examples of force carriers. There are mainly four force carriers we will discuss in next slide. Okay, now we will discuss about how we can relate this to the high energy physics. Okay, basically it explains the behavior of particles. Okay, your standard model basically illustrate about the behavior of particles, how particles behave to each other. Okay, how they produced in high energy collision, because you know that we are producing particles at LHC by colliding two atoms or two particles, you can say two proton beams, with a very high speed, nearly equals to the speed of light. They have very high energy, and after an high collision they produce daughter, you can say daughter particles, dead particles we have to discuss, and this is our main work. Such work is going and doing at LHC, the Large Hadron Collider. Now let's overview some properties and of our particles like quarks. And you know that everybody in the universe, every particle in the universe having their antiparticle also. Okay, so if quarks exist by standard model, then there should be anti-quarks. Okay, so the quarks, basically you can say how you can define the fundamental particle quark. You can define it as it's basically the building block of protons and neutrons. Okay, you know that inside proton there is two up quarks and one down quark. Similarly, in neutron there is two down quark and one up quark. Okay, so proton is a combination of three quarks and neutron also. So the main, there are six quarks, and what are their names? So the quarks are up quark, down, strange, charm, top, and bottom. These are the total six quarks, okay, in the standard model, which are yet the fundamental particles. Because these are quarks, so there are antiquarks also. So the properties of antiquarks is, okay, all masses is same, all things are same, but having opposite charge. Okay, along with the quark, as I told you, there are some leptons. Okay, so the properties of leptons we will discuss. So the leptons, first you know that what are leptons. So the leptons includes like electrons, muons, and neutrinos. These are basically the leptons. Okay, you can also say that tau on. Okay, tau is also a quark, muon is also a quark, electron. Okay, it basically your leptons, they do not participate into the strong interaction because they are neutrino based. Because you know that every lepton has their neutrino also, like electron has electron neutrino, mu has muon neutrino, tau has tau neutrino. Okay, so leptons do not participate in the strong interaction. Understood? Now let's move, because there are leptons, which are the elementary particles. We have also some anti-leptons. So the anti-leptons are basically having same mass, same aspects, only the charge is opposite. So this is our introduction session. Let's move towards the fundamental forces. As I mentioned you before, there are total four fundamental forces in the universe, in the nature. The first one is the gravitational force. What is the gravitational force? Gravitational force is basically the weakest force of the all four fundamental forces of nature. because you know that gravitational force having a long range means long distance. You know that we are feeling gravitational force everywhere if we went to the mountain, top of the mountain. Even we also, okay, we feel the gravitational force there because the range is a long distance for the case of gravitational force. Because the range is so long, so that's why it's basically the weakest force of the all four forces. This force is governs the motion of planets, stars, galaxies. You already know the force between our planets, between our stars and the galaxies all around in the Milky Way or in the universe are basically the gravitational force between planets, stars and galaxies. Because you know that the distance of the planets, stars and galaxies are in the light years. And light years is a very, very, very long distance. Okay? And this force is negligible at particle level. Definitely, if this force is for long range, then obviously this force is not for the particle level. That means this force is for macro level, large macro level, not for micro level. So now let's move on towards our next fundamental force, and our next fundamental force is basically the strong nuclear force. What is the strong nuclear force? As the name stands strong, so it's definitely a strong force. It's basically the strongest force, okay, between all the four fundamental forces. Because it's a strong force, so their range is very, very short. Okay, so it's the strongest force, but it has short distance force. Understood? It binds quark together in proton and neutrons. As I mentioned before, that proton has two up quark and one down quark. So the inside proton, quarks are bounded into the proton by the strong nuclear force, because you know that the dimension of proton and neutron in an atom in a nucleus is 10 raised to power minus 15. Means femtometers. Very short range. Okay, now here you can see basically your strong force is crucial, okay, for understanding jet production, okay, in particle physics. So this strong force is very, very important. This is very crucial for understanding the jet production in particle collision, because in this presentation our main task is to discuss the jet production. So our main target is basically the strong nuclear force. Now let's move on towards the third force, and our third force is basically the electromagnetic force. And what is electromagnetic force? As the name stands for electromagnetic. Okay, and electromagnetic is a combination of two words. Electro means electricity and magnetic means magnetic field. Okay, so electricity is only there when there are charges. Without charges, there is no electric field, you can say. So because this is electromagnetic field, so the origin of electromagnetic force is basically the charges. Yes, you are right. So this electromagnetic force basically acts between the charged particles, not between the neutral particles. And this electromagnetic force is responsible for the phenomena of electricity, because you know that whenever there are charges, there should be electricity. And whenever there is electricity, there must be some magnetic field, because you know that moving charges produces magnetic field, and magnetic field also produces electric field, vice versa. Okay, and this electromagnetic force is responsible for light. Okay, and the range of electromagnetic force is infinite range, stronger than gravity. You know that gravitational force is a long distance force, but beyond gravitational force, there is another force which has infinite range, infinite distance. It spreads in infinite universe, and that force is basically the electromagnetic force. And our last force is basically the weak nuclear force. And as the name stands weak, so this force is basically the weak force. This weak force is responsible for the radioactive decay for neutrinos interaction. This force is always there whenever there is neutrino interaction includes. And this force is where whenever there is some beta decay. Okay, so you can say this force is responsible for the radioactive decay, means beta decay. And this force acts at subatomic scale, means fundamental scale, relevant to particles interaction in high energy physics. Our next slide is basically we will discuss about the Large Hadron Collider LHC, okay, which is the most world largest and the most powerful particle accelerator, okay, which is located at Geneva, Switzerland, across the border of France and Switzerland. Understood? It's basically located at CERN. It's spacing along 27 kilometers of circumference. Okay, and it operates at unpredictable high energies. As I mentioned before, the minimum is 0.9 for the case of proton-proton collision, up to 13 tera-electron volt yet achieved. Okay, so the role in high energy physics of LHC is basically the collides protons. As I mentioned you before, our task is to collide our particles like protons, hydrogen atoms, proton at nearly speed of light. Okay, and recreate the conditions like the Big Bang, how our universe came into being, because we know that Big Bang is such a similar case where your universe came into being after some collision. Okay, your particles came spread and spread, so we are looking the similar recreate the conditions of the Big Bang, doing experiments at LHC. Key for discoveries of Large Hadron Collider is basically the Higgs boson, which is recently achieved and discovered, and understanding the jet dependence in the particle production. What is jet production? We will discuss in further slide. As you can see, this is a large 27 kilometer circumference spanning of the LHC, which has four detectors: CMS, LS, Atlas, and LHCb. Your proton beam is first accelerated, okay, by an hydrogen cylinder. After moving into the booster, it gains some velocity, okay, then it moves towards the PS, proton synchrotron. Here, the speed again increases more. We provide external electric field, okay. It circulates in proton cyclotron. After many seconds, after gaining much speed, move towards the SPS, super proton synchrotron, and finally move towards the Large Hadron Collider, which is 27 kilometer, which contains three country borders like France, Switzerland, and Germany near Geneva. So this is the LS experiment at LHC. So what is basically the LS experiment? LS detector, as I mentioned you, is one of the detector which is installed in between the Large Hadron Collider. Okay, this is basically a dedicated heavy ion detector. Heavy ions means more ions. Okay, so LS is working on heavy ion detectors at LHC. LS stands for a Large Ion Collider Experiment. As the name stands, large ion means heavy ions colliding in LS detector, and we measure after them. This is optimized for studying the quark-gluon plasma state and the properties of strongly interacting matter. Okay, this is basically optimized for the QGP, quark-gluon plasma state. How your universe came into being. Next, the purpose. So LS basically focuses on the proton-proton collision and the heavy ion collision like lead-lead, xenon-xenon, argon-argon. These are heavy ions. This investigates the formation and behavior of hot, dense matter in the earlier universe. Understood? And this detector is very crucial for understanding the multiplicity, which is one of the factor which we have to discuss in our this presentation. As I told you in the starting of this presentation, that we have to discuss the particles multiplicity distribution, pseudo-rapidity, and lastly the transverse momentum distribution. So LS is basically best and crucial for understanding the multiplicity and the charge particle production in high energy physics. So you can see this is an illustration of an LS detector inside this. This is TCP where your particles collide. One proton beam is coming from this direction, another proton beam is coming into the opposite direction, and they have to collide in between these detectors. After collision, then we will measure the daughter particles. Now, let's move on towards the charge particle production. How a charge particle produced. Okay, so the definition of the creation of the charge particles like protons and electrons, you know that these both are the charge particles during high energy collision, such as those in proton-proton, collision at LHC. Charge particles, how they create the creation of charged particles basically by colliding with high energies. Okay, when they collide, you know that because they have a very much speed, so because they are particles, because they gain much energy, so all the energy of that particles by moving with a velocity of speed of light approximately. So they have energy, and when they collide, you know that by the relation of Einstein, E is equals to mc square, all the energy is converted into the mass. So all the energy that proton, any particle has before collision, after colliding, they have after collision, they are converted all the energy into the mass, and that mass is basically the residual particles, means daughter particles. And our work at LHC is to discuss those fundamental particles that came into being after the collisions of other particles. Understood? So a key concept is to discuss their multiplicity. And what is the multiplicity? So the multiplicity is basically the total number of charged particles produced in a collision. As I mentioned you that charge particle collide, after the collision, the total number of how many charge particles produced after collision means how many daughter particles produced after the collision. This is so called as the multiplicity. Okay, it reflects the events, complexity, and energy transfer. Our next task is to discuss their pseudo-rapidity represented by symbol eta. What is pseudo-rapidity of the particle? Basically, pseudo-rapidity describes the angle of the particle emission relative to the beam axis. What is beam axis? As I mentioned you that this is beam axis, you can see. Here your particle is coming in this direction, here your particle is coming in this direction. So this line is basically the beam axis. This orange line you can see. So, pseudo-rapidity is basically the angle between the particle emission, at which angle your particle emitted are relative to the beam axis. This is so called as the eta means pseudo-rapidity. Because this is concerned with the angle, so it is important for understanding the angular distribution of the particle. And our last concept which we have to discuss of the charge particle production is basically the transverse momentum, which is denoted by pt. So what is transverse momentum? You must have to know that. So the transverse momentum is basically the momentum of the particles perpendicular to the beamline. And now what is beamline? Beamline is same as the beam axis. As I saw you what is beam axis, same as the beamline. So transverse momentum shows you basically the momentum of the particle but perpendicular to the beamline. This is so called as the transverse momentum pt, a key variable for exploring the particle energy and jet formation. So transverse momentum is very very crucial. That's why, because we have to watch on dependence of jet formation, that's why we have to know how what is the transverse momentum of that particles after colliding. So the literature review of our presentation of the charged particle production mechanism. So the mechanism is key studies exploring charged particles production in proton-proton collision. In this scenario, we are using proton and proton. So our basically the production mechanism is hard scattering. First of all, where is hard scattering and what is hard scattering? Hard scattering is always involves high momentum transfer between quarks and gluons. Quarks are the fundamental particle and gluon is basically the fundamental force. You know that. We already discussed about the fundamental particles and their forces. So where are the hard scattering? So hard scattering basically involves high momentum transfer, means high PT, because you know that PT is basically the momentum perpendicular to the beam axis. So hard scattering means high momentum transfer between the particles and their forces like quarks and gluons. And this hard scattering is basically leads to the formation of jets and energetic particles. If hard scattering, then more jet formation and more energetic particles produced after collision. And what is soft scattering? Totally opposite of the hard scattering. As you know that hard scattering is whenever there is high momentum transfer, so the soft scattering is occurs at the low momentum transfer. So in soft scattering, your momentum transfer is lowered. Okay, because your momentum transfer is low, so the formation of jets is also weak, and there is less energetic particles produced. So you can see produces large number of low energetic particles. Means low energetic particles produces more, contributing to the multiplicity. Now, relevant to our research is studies analyzing the correlation between the collision energies and particle production and focuses on understanding the role of jets in charged particle production. So, this is our relevant research in this presentation. We will analyze the correlation between the energies. We will increase, we will decrease, we will make a middle energy. In this research, we will using the minimum 0.9 tera electron volts, middle energy is 7 tera electron volts, and the max energy is 13 tera electron volt energy. So we are analyzing the correlation between the collision energies and the charged particle production made to discuss their multiplicity, pseudo-rapidity, transverse momentum, and then we have to focus on the role of the understanding the role of jets in the charged particle production. Now move on towards the jet production. What is jet production? So the definition starts with the definition is basically jets are sprays of particles. Sprays. You know that what is spray? Like water spray. Let's assume you have a water bottle, water spray bottle. Once you spray, you know that your water speckles out from a nozzle and moves all around in the space, having more sub water molecules. So this is so called as spray. So in jet production, jets are sprays of particles. Your water bottle basically has water particles. Okay, but in jet production, let's basically, this is just for example, jets are sprays of particles, means many particles are now spreading in the space like a shape of jet. This is a shape of jet, you can see. You know that here, like suppose this is a nozzle, and whenever this is sprayed, this is move in this jet direction, and inside this jet there is number of particles. So spray of particles basically so called as jets. This is resulting for hydronization, okay, of quarks and gluons produced in the high energy physics. So jets are very crucial for the hydronization. Now what are their significance? You can see one proton beam is coming in this direction, another proton beam is coming in this direction. Whenever they collide, okay, at a point, this is beamline, and this is angles, they spread into the space. So the angle between beamline, okay, is basically the what is basically the pseudo rapidity eta, and the angle between beamline perpendicular to the momentum, this is the transverse momentum, and the number of particle total number of particle produced is basically the multiplicity. So these are the sprays of particles they produced in a form of jets after collision. So what are their significance in particle physics? Probing the fundamental forces. So jets are basically probe the fundamental, tells us about the fundamental force. Jets serve as crucial tool to study the strong force and its interaction. As I mentioned you before, in this presentation we will mainly discuss about the strong force because we are dealing with the proton and proton. Because you know that in proton and proton we are concerned with the strong force. And the second significance in particle physics of jets is basically the energy measurement. Basically, understanding jet production helps in measuring the energy and momentum of the colliding particle. We can easily understand the jet production helps, okay, in measuring the energies of dead particles, of parent particles, and momentum of the colliding particles. What are their experimental observations? So it analyzes of jet properties, okay, provides insight into the initial states of the collision and the dynamic of the final state, okay, because you know that jets, it make jets, so easily in we can easily see the insights into the initial states by making some imaginary lines beyond, okay, and before that, after making that, we can see easily the insights into the initial state of the collision, okay, where particles collide. Means initial state means we can easily check the initial particle produced, the first particle produced after collision, because particles produced after collision has a very short time. We cannot directly measure that particles because that decay particle further decay and move into jets. So by constructing the imaginary lines before, we can easily see the insights of, okay, the initial state of the collision and the dynamics of the final state obviously also. Relevance to the LHC is basically at the LHC, jet production is key aspect of various experiments, including studies related to Higgs bosons production. So in Higgs boson productions, jet production is very crucial. Okay, and for new physics researches, definitely this is very important. Now let's move on our next model. So the model we are using is basically the HIJING model. HIJING, which stands for Heavy Ion Jet Interaction Generator. It is basically a Monte Carlo event generator which is used for simulating high energy nuclear collisions data. So we are using the HIJING model. So what is HIJING model? As I told you, this is basically the heavy ion jet interaction generator. It combines soft and hard process scattering both. You already know what is soft and hard scattering we discussed in previous slide. So the HIJING model, it combines both the soft and the hard processes to describe the particle productions in heavy ion collision. In our concern, we are concerned with the proton-proton collision. Okay. So the key features, what are the key features? So the first is the jet formation. Yes, the jet formation. The model accounts for the fragmentation of quarks and gluons into jets. So this model is very important because this accounts for the fragmentations, means elementary particles like quarks and gluons into jets. Undrilling events. HIJING incorporate soft processes that contribute to undrilling events in high energy collision. Basically, HIJING incorporates these soft processes. This is very important thing. What are their applications? Applications in our study is basically we use simulation of charge particle production. We use the HIJING model in our presentation in our project is we use to simulate events in proton-proton collision. We study the multiplicity, pseudo-rapidity and the transverse momentum distribution. Okay, in our this report, how we compare data. So the results from HIJING simulation after simulating our proton-proton collision and check their multiplicity, pseudo-rapidity and transverse momentum distribution, we move towards the data comparison. So for the case of data comparison concern, we results from the HIJING simulation which we gained we compare that data with the experimental data from the LHC to validate the model and enhance the understanding of the particle production mechanism. What is the importance of the HIJING model? The HIJING model plays a crucial role in predicting the outcomes and guiding experimental investigation in the high energy physics. So the HIJING model is very important for predicting the outcomes, means event generators, and guiding the experimental investigate of the high energy physics, or you can say the particle physics. Understood? Now let's move on our results and discussions session. So the methodology simulation with HIJING, which we simulate investigate of the charge particle production in proton-proton collision. We are taking three energies. The minimum energy in pp is basically the 0.9 TeV, then we use 7 TeV, and the max, which is the 13 TeV. We investigate the charge particle production in proton-proton collision at these energies using heavy ion jet interaction generator, means HIJING. Simulate jet generation in high energy collision. First of all, what we supposed to do, we set it our center of mass energy at 0.9. then 7, then 13 GeV. Then we define our collision system, which is definitely proton and proton. Then we specify the number of events to check the statistical significance. Then we initialize the transverse momentum and impact parameter. Okay. Then we book the histogram, make the plots of the multiplicity, pseudo-rapidity, and the transverse momentum. Then we check the jet dependence analysis. Jet dependence in our case varied as a value at a 1 means a 1, the other is on means default, and off. Okay, on, which is default, off, and at value 1 to assess its impact on particle multiplicity and transverse momentum. Then we will check the multiplicity, which is the total number of charged particles produced per event. Then we discuss the pseudo-rapidity distribution, which is basically the angular distribution of the charged particle, angle between the beam axis and the charged particle produced. And lastly, the transverse momentum spectra we plot, which is that basically transverse momentum is basically the momentum of the charged particle perpendicular to the beam line. So graphs of multiplicity, pseudo-rapidity, and transverse momentum to illustrate the key findings. So let's move to Earth next, to our graphs. So these are our results for the case of multiplicity results in proton and proton collision. As you can see, along x-axis is basically the multiplicity at different energies. Like first of all, we are using 0.9 TeV, then 70 eV, then 13 TeV. The Z dependence is set it as default value, means Z is on. Z set it as off, means Z0, Z off, and Z value set to 1. Similar cases for 70 eV energy and similar case for the 13 TeV energy. Along y-axis is basically the probability of the multiplicity. So what we can conclude from these results, basically you can see the curves shows feature a peak at low multiplicity. You can see there is a peak in all the graphs, and that peak is basically at the low multiplicity. So what you can conclude by this, okay, at low multiplicity there is a feature peak, okay, followed by a rapid decrease. Then there is a rapid decrease. You can see sudden peak, then a rapid decrease in all the collision energies. Rapid decrease. There is a peak at low multiplicity. What it indicates is basically indicates that events with fewer particles are more frequent. Okay, that events with fewer particles are more frequent, means the probability is more at low particles. The probability of multiplicity is high at low multiplicity. Understood? Now also you can see that the events which have fewer particles, here the fewer particles 25 you can see, here fewer particles 25 you can see, here also around 5 or 8. So fewer particles are more frequent. This result first came. And another thing, as the collision energy increase, this is low energy, then high, then most energy. So as the collision energy increase from left to right graphs, you can see the peak shifts towards the high multiplicity value. Okay, you can see the peaks shift towards the high multiplicity value. as the energy increases. This is first 150, then move towards, you can see, goes around about 180, 200. Then this is beyond, there is also above the 200. So as the collision energy increase, the peak shift towards the higher multiplicity. So here the peak is high, but once you increase the energy, you can see it peaks. Your peaks shift towards the higher multiplicity. The distribution tail extends further for higher energies. Also, you can see what are the distribution tails. These are the distribution tails. When you high the energy, the distribution tails extends further. Okay, you can see in this, here is at, you can see at 70. Now here your tail extend to 100, and here you can see tail extend to 125. Here is 110. Here you can see around 150, and here you can see 175. Again, this is a black. When jet is on, your tail distribution extend to the higher energies. What it shows, basically showing that higher multiplicity events become more likely. Okay, shows that higher multiplicity events becomes more likely as the collision energy increases, and higher collision energies allows for production of more particles. So you can see that higher collision energy like 13 TeV, which is the higher collision energies, this allows you the production of more particles, because you can see here, um, um, because showing that high multiplicity events, okay, become more likely as the energy increases. So the last result is basically across all energies. So the jet dependence we have to discuss in this. So all the energies means when you set your value jet on, consistently show a broader distribution. Okay, indicates high particle production compared to when your jet is set as off, and whenever your jet is set, okay, at value 1. So you can see whenever your jet is off, you can see that shows a broader distribution, indicates high particle produced when your jet is set it as off. Okay, mainly you can see at 10 is per minus 2 up to high particle production. This is also high particle production. You can see here low particle production, because low energy once you increase the energy, or you can see whenever your jet is set it as value 1 on, so you can see more particle, higher particle production as compared to when your jet is 1 and jet is off. Jet is 1, jet is off, jet is 1, jet is off. So these are the results, multiplicity results in proton-proton collision. So what are these pseudo-rapidity results in proton and proton collision? Is here are the results. In the x-axis is basically the pseudo-rapidity eta distribution, and on y-axis is basically the number of events. Okay, and this, so the particle production. So in these graphs, again you can see dependence of different energies at 0.9, at 7 and 13 TeV, along with the jet dependence, jet on, jet off, jet 1 set similar in these cases. So first of all, the particle production. So the results. So first of all, we discuss the plot demo. You can see the plot demonstrates that most particles produced in proton-proton collision are considered in the central region, symmetric around theta equals to 0. You can see most particle produced in the central region, because you can see here is peak at the center at eta equals to 0, means pseudo rapidity at eta equals to 0. There are the most number of particles produced, means concentrated into the central region. You can say symmetric. Okay, symmetric, because forward and backward is same. So you can say this is symmetric, and decreases with increasing eta mod. So with increasing the value in forward direction, or either increasing the value of eta in the backward direction, your value decreases means the number of particle production decreases, but this is maximum at the central value at eta equals to 0. In all the energies, the graph is same. You can see at central, the charge particle production is more. Either the jet is set on, 1 and off. There is more number of particle production at the center at eta equals to 0 and goes decrease when increasing eta mod. So energy dependence, you can see as the collision energy increases from 0.9 to 13 TeV, the height of the central peak rises. Okay, the height of the central peak rises. You can see suggesting a greater particle production at high energy. So you can see this peak is sharp, this is wider peak, and this is more wider. So by increasing the amount of energies of the collision, the height and the width of basically at the central peak rise illustrates basically the greater particle produced. So here the greater particle produced when increasing the energy. And the jet dependence of pseudo-rapidity is basically the jet dependence. We can see when jet is set it as off, it has high peak, similar high peak here, similarly high peak here. So the JD when jet set as on, data set shows the highest peak, highest particle density. Okay, highest peak means highest particle density. You can see here is the density, here is the density means high peak density when your jet is set it as on, and when your jet is set it as value 1, this is an intermediate density, and when your jet is set as off, then it is the lowest density. You can see with this red dot plot. So JD data set shows the highest particle density across all pseudo rapidity ranges, followed by J1, then J1, and then J0, then J1, then J0, JD, J1, J0. Okay. This ordering suggests that JD events contain more overall activity. JD has more number of particles produced. Okay, so the jet dependence is very crucial. You can see whenever you set your jet on, you can see most particle produced. Whenever you set your jet value 1, it here, and whenever you can set your jet off, you can see there is low number of particle production. Okay, so jet dependence, that's why very crucial. This ordering suggests that the JD events contain more overall activity, while J0 events are relatively less active. You can see this is less active. Now let's move our final results. Our final results is basically the transverse momentum results in proton-proton collision. So in x-axis you can see is basically the PT value in giga electron volt per C, and in y-axis basically the per number of events and this scenario. And again you have to increase your energy from 0.9 up to 7 towards max 13 TeV. Along we have to check their jet dependence and jet value set as on, value off, and jet dependence set as value 1. So what our basically results are, this spectra decreases rapidly with increasing PT. You can see by increasing the value of PT, the spectra decreases. You can see in this graph at 0.9 TeV and 7 TeV, same scenario, and at 13 TeV, there is a decrease in rapidly in, okay, by increasing the PT value. But it indicates that low momentum particles are more common than high momentum particles. Okay, because at low momentum, at low PT value, you can say there is a maximum particle production. So you can indicate that low momentum particles are most common than high momentum particles. So low momentum particles are more produced after in the collision. Okay, and high momentum particles are lessly produced, very low ratio. So in collision, after collision at of proton and proton at LHC, your low momentum particles are more produced, okay, at low pt value. Okay, when the increase in pt, with the increase in the transverse momentum, then your higher particle then your higher momentum particles are then produced. Okay, so let's see the energy dependence. This scenario is same for this and this. Let's check the energy dependence. So with increasing collision energy, the distribution exhibits a longer tail at higher pt. So you can see this is low energy, so the tails stops at, mainly you can see it is low about at 16 to 18. When you increase energy up to 70 ev, you can see it, the tail extends to more events, more particles at higher pt. Okay, high momentum. Okay, and this is basically, you can see at maximum energy 13 TeV, which is you can see that with increasing the collision energy, here the 13 TeV, the collision energy, the distribution exhibits long tail. Here is the tail long. It also extends beyond 20. Okay, beyond 20, after 20. Okay, so with increasing the collision energy, the distribution exhibits longer tail at pt value, because you know that the low momentum particles are most common than high momentum particles, because low momentum particles produce more. Okay, so by increasing the energies, so what you conclude that your higher with the increasing diffusion energies, the distribution exhibits towards the longer tail towards the pt value. Okay, this trend reflects the increased phase space for higher momentum particles produced at the high energies. So you can conclude that uh, by increasing the collision energies, you can easily move towards, you can easily produce the space for the particles, means high momentum particles. So by increasing the energies, you can easily produce the high momentum particles. Okay, because you know that low momentum particles are most common, because you can see in this. But by increasing the amount of energies in of the collision, you can move on towards the high momentum. So at high energies, you can easily probe with the so at high energy, you can easily probe with the high momentum particles. Okay, so this trend reflects in the, it reflects the increased phase space for the high momentum particle production at high energy. So you can conclude that the high momentum particles produced at the high energies, and low momentum particles already you know that are most common at lower pt value. This is either for low momentum is either for low energy and high energy, but your high energy is only for the high momentum is only for the case of high energy. And lastly, let's check the jet dependence. So the JD data, this constantly show that whenever your jet is set as on, the black decay curve shows basically when your jet is set as value one, sorry, on. So the JD data constantly shows higher yield across PT range. You can see this black is high PT range. Okay, similarly, this black you can see higher yield across the PT range corresponding to J0 and J1. Okay, suggest that JD events are associated with more active collisions. So JD has again most active collisions, as you see in the pseudo-rapidity distribution. So again in the transverse momentum results, you can see that the JD data constantly shows yield across the PT range compared to J0, and when your jet is set as 0, and when off means, and when your jet is set as 1. What it suggests that JD events are associated are more active collisions. Okay, whereas J0 shows the lowest yield, as you can see from this red curve. It is lowest yield, and J1 exhibits intermediate yield. So, whenever your jet is on, it is associated with the more active collision. So that's why jet dependence is very crucial. Okay, for this. So these are our results for transverse momentum. We also discussed our results for the pseudo-rapidity, and we also discussed our results for the multiplicity. So that's all for our research report of jet dependence particle physics. Okay, this is our conclusion part. Multiplicity. Basically, we discuss the charge particle multiplicity increases. Our results conclusion is this. Charge particle multiplicity increases with higher center of mass energies, means whenever you increase the energies, your charge particle multiplicity also increases. Understood? Particle influenced by the jet production. Also by setting your value jet on, higher multiplicity. Then pseudo-rapidity distribution shows a strong energy dependence with wider distribution at high energies. You can also see in pseudo-rapidity results like whenever we increase the energies, shows a stronger energy dependence and its wider distribution at higher energy, means most particle produced at the higher energies. Then transverse momentum. The transverse momentum spectra you see before broaden with increasing collision energies indicates the production of more energetic particles, means high momentum particles, because you know that high momentum particles are produced at high energies. Okay, so high energies, high momentum particles are produced. So in transverse momentum, you can see by increasing the energies, it indicates production of more energetic particles at higher energies. Then we discuss all the aspects of the jet production. Plays a crucial role for enhancing the production of high momentum particles, because you know that whenever your jet is off, low momentum particles are mainly produced. Okay, low momentum particles are mainly produced. Whenever your jet is set as 1 or jet is set it as on, you can see that the uh, production enhances up to high momentum particles. Okay, at higher energies also. Events with jet production exhibits broader PT distributions. So the events with the jet production exhibits broader PT distribution, reflecting greater energy transfer. Physics. What are the physics insights? So it's basically understanding jet's contribution helps in modeling particle physics conclusions more accurately, which is essential for studying high energy phenomena such as those observed at the LHC. Understood? So this study provides deeper insights into the charged particles production mechanism and emphasizes the critical role for jets in sharpening the particle production landscape in proton-proton collision. So this is the study results and the conclusion of our research reports of the jet dependence of proton-proton collision at LHC Energies. So this is our future framework, extended analysis of jet production, future research into the details mechanism of jet production. In future, we will research into the detailed mechanism of jet production in high energy collision. We could provide more insights into the particle generator and energy transfer processes. And then we will comparison with other collision types, like future studies can include proton nucleus, like we will collide proton lead, you can say, and nucleus like lead collision to explore differences in charge particle protection across varying systems. Understood? And then we will high energy collisions. We will investigate the collision at even higher energies. Example: future LHC upgrade. If there is some more energy above 13 TeV, definitely we will use them and use to observe the particle protection trends and new physics phenomena. Then inclusion of more advanced models using more synthetic simulation model alongside with HIJING for a more comprehensive understanding of the complex collision dynamics. Okay, then experimental data correlation, correlating simulation results with experimental data from LHC detector. Understood? Like LS, we will also correlating simulation results with experimental data from LS. Okay, to validate prediction and improve model accuracy. So these are the acknowledged by our professors, Dr. Ali Zaman, okay, for his valuable guidance, supervision, and support throughout this research project. And then our course instructor, Dr. Usmat Bassum, for their assistance in deepening my understanding of particle physics and providing insights, feedback, then collaborate and fellow students for their constructive discussion and contribution that enriches the study, and family and friends for their unwavering encouragement and motivation during the completion of this work. So these are the references of the images and figures used in our presentation of this project. Thanks for watching. I sincerely appreciate your time and attention. I'm grateful for your opportunity to present my work, and I welcome any question or feedback you can leave in the comments below. So thanks for watching. Allah Hafiz.